Okay, so what we're going to be talking about today is instantaneous velocities from position time graphs and displacement from finding areas underneath velocity time graphs. So let's go ahead and begin. You don't have to draw this, but I am just going to share a little story with you. So let's say that there is a dog that is chasing you, and so of course you're going to run away, and you're going at a velocity or a speed of 6 meters per second. Along your run to the house, you start to get a little tired, and so your pace goes to more of a little bit slower, so it's 2 meters per second. Then you gain a little bit of motivation because you're almost there, so you run a little bit faster, and now you're at 8 meters per second speed. Each of these 3 speeds are your instantaneous speeds at that moment. So it's any speed at any particular moment. That is the instantaneous speed. If there is a vector involved, then we can call this your instantaneous velocity. So remember, velocity is just, again, at any particular moment makes it instantaneous. It is not an average velocity. So for example, the distance from the house from where the person started is 1,000 meters. It took you 200 seconds to get home, so all you would need to do to find the average velocity would be to divide the total distance traveled by the time that you traveled, the unit of time that you traveled the entire 1,000 meters, which would then be a positive 5 meters per second to the right direction. Your instantaneous speed, as a recap, is just any speed at any instant. You could get this information by viewing the speedometer or any other device that can electronically get the data. Instantaneous velocity is the amount of displacement at any instant. Now, how do you find instantaneous velocity another way? So instead of it being given to you by the speedometer, you do have a few options. So one option is, if you know that the velocity is constant, the average would be the change of x over change of t, so that would just pretty much be your instantaneous velocity. Because your velocity is constant, for example, down here, if this person was running 6 meters per second at every moment, then you know that your average is a 6 meter per second, and it is the same as your instantaneous velocity. Pretty easy. Now, everything is not always that easy. So option 2. The next part is to find the slope of the tangent of the position versus time graph. So if you have access to the position versus time graph, then all you need to know is that the slope is the instantaneous velocity at whatever time you wish to figure out what the velocity is. So remember, slope is the change in y, or the rise, over the change in x, which is the run. So let's go ahead and take a look at this. Find the instantaneous velocity at 1 second of this graph. So we have position over here and time. So the first step that you're going to want to do is draw the tangent touching the curve at the point of interest. So 1 second is right there, so I went ahead and drew the line a little bit more so it could pop and you can see that. Step 2 is to find 2 points on the tangent to calculate the slope. So here it's already denoted as 0.50, and then down here 2 minus 6. These are my 2 coordinates that are along this tangent. So it's not the one that is the curved line of the position versus time. You're actually making a line that is just touching right on that 1 second and even sides on both sides of the slope. And what you're going to do is you're going to take these 2 coordinates and you're going to calculate the slope with these 2 new points that you have. So remember, that is rise over run. So you would take your y points, your velocity would then, your instantaneous velocity would then be the change in y, which is minus 6, negative 6 minus 0, and then 2 minus 0.5. And that would give you a velocity of negative 4 meters per second. Let's use the same graph to find the instantaneous velocity at a different time. So the last one that we just did was at 1 second. Let's find 1.5 seconds. So that would be right about here. So the first step that you're going to want to do is, again, to draw the tangent. and here it is. It's illuminated a little bit brighter. And then you are going to need to find 2 points on the tangent. And the best thing to do with this is that you want to try to find points that are further apart from each other than closer, so then that way your slope is defined. So here are our points that we chose. It is going to be 0.750, and then of course the 1.5 is very easy to figure out because it's 4.5. So from this you would just solve the slope, and your answer would be that the instantaneous velocity is -6 meters per second. Now, another thing that you can do when you're looking at a velocity time graph, so now we're moving to velocity time graphs, the area underneath the line, so the area bound by the line and the axes, actually represents the displacement of the object. Pretty cool. So all you need to do is know how to find the area on a graph. So you're going to be met with a few different shapes, right? So if you know the area of a rectangle, the triangle, and the trapezoid. B is the base, and H is the height. So usually your base is obviously going to be your x-axis, and your H is going to be your y-axis. So this is how you find the areas for these 3 shapes. The area of a triangle. If you were given this graph, you know that all this area here is going to be the base times the height. And so if you go over here and you just look, you see that the base is 6 seconds. And you multiply that by 30, which is the height, 30 meters per second. When you multiply that, you get an area of 180 meters. Pretty easy. So that is what it states, is that the object was displaced 180 meters during the first 6 seconds of motion. Here's another example. Area of a triangle. So we know that the area of a triangle is 1/2 times the base times the height. Here is our graph, and the purple area is the part that we are trying to figure out what the displacement is of the object from 0 to 4 seconds. So we have our equation over here with everything plugged in, and your total should be 80 meters for the area. This means that the object was displaced 80 meters during the first 4 seconds of motion. An area for a trapezoid. You have a few options. You can use the equation for a trapezoid, which is 1/2 times the base times height number 1 plus height number 2. For example here, because the trapezoid is just this area here, so you're trying to figure out the displacement between seconds 1 through 3. So that's only actually within 2 seconds. In order to find that, you would need to know what this point is right here for H1, the second point here for H2, and you would know your base, and you just plug everything in, and you should get an area of 40 meters. The object was displaced 40 meters during the time interval from 1 second to 3 seconds. Option number 2, in order to find the area of a trapezoid, is to find the sum of the areas of the contained rectangle and triangle. So let's say you don't remember how to find the area of a trapezoid. All you need to do then is to break it up into 2 different shapes that maybe, hopefully, you do know the area for. So here you have the triangle, and that's the area of a triangle. And then you also have the area for a rectangle, which is base times height. So between seconds 1 through 3, which is again 2 seconds, just go ahead and find the area for the triangle section and for the rectangle section. And your total area would be the addition of both of those areas, therefore equaling 40 meters. Go ahead and pause the video, try to find the areas of both of these graphs, and then start the video up to see the answer. The answer for practice A is 120 meters. The displacement for B is 90 meters between 3rd second and the 6th second. Here's another one you can pause and try to find the area or displacement of the object. The answers are 5 meters and 45 meters. Here's another one. So remember, this one is a trapezoid, or you can cut it into a triangle and rectangle. Your answers are 25 meters and 40 meters. Okay, so your home phone is pretty much just to bring your TNOTES. All this other stuff right here is just for you to get more background information and just to see how your book lays out some problems. So read pages 32, or just page 32. Try doing the worked example on page 33. Check your work with the book's answer. See how they're thinking about when they're working through the problems. Read pages 33 through 34, and that starts with describing motion with the graph part 2. Do the worked problems that you see, and remember, you don't need to show me this, just the TNOTES on the next class. All right.